Hello, this is Mr. Craig, and this is day 15 examples. And today we're going to talk about electrolytes or ionic compounds that dissociate into ions. That's what an electrolyte is. And solution concentrations. And we'll make solution concentrations from a solid. We'll make a solution concentration that we will dilute from a stock concentration. And I think we'll then make a stock solution from a solid, and then we'll dilute that down. So we've got a couple different things that we're going to talk about today. And I have some graphics, and I believe I may have printed these out for you so you can refer to those as we talk about, or as I talk about these topics today. All right, question number 1. Show how each of the following strong electrolytes breaks up into component ions upon dissolving in water by drawing molecular level pictures. Don't worry about the pictures. I'm more interested in you showing me how these dissociate. Also, when I talk about strong, don't be so concerned about what the word strong means at this point. When we talk about acids and bases, strong will be defined at that point, and at this point, what I want you to realize is that everything that I'm giving you, if I place it in water, will dissociate completely, or at least there'll be some degree of dissociation. So you'll find out later on that some of these are not very strong, but for the purpose of the lecture today, I want you to treat it as it is strong. So if you're looking at this video again right before the AP exam, you're going to be able to look at some of these and say, oh, that's not strong, according to solubility rules. But that's okay. All right, so let's go ahead and get started here. The first thing that I want you to do is drawing a molecular level picture. We're not so concerned about that, but I do want you to know how these dissociate. So if I take these and place it into water, we want these to break up into ions. So that's what an electrolyte is. When you drink Gatorade or Powerade or whatever sports drink that you may partake in, when it says it has electrolytes, what it's mainly talking about is the electrolytes that you are losing while you're exercising, like sodium, potassium. Not real sure what else is pretty vital there. Those are the two biggies that we care about, especially with the sodium-potassium pump. All right, so looking at the calcium phosphate, our first example here, we have calcium and phosphate. Now, do recall from General Chem that when we have a polyatomic ion, again, like in an earlier discussion, you need to recognize what the polyatomics are, and you need to be able to name them and know what the charge is. Because when we place these solids into water, they will dissociate or break apart into its ions, and an ion, by definition, is an aqueous thing that has a charge. So what's going to happen is this calcium on the phosphate is actually going to break apart, and we're going to get 3 calcium ions from this calcium phosphate. And then the phosphate will also break apart, and we'll have 2 phosphates. That's a negative 3. Okay, so again, what we've done here, and we'll talk a little bit later on in the year, but if I were to ask you, what is the Van Hoff factor for this? If you said 5, you're in great shape. All right, so we'll talk about Van Hoff factor a little bit later on. That's actually one of the last topics that we'll talk about right before the AP exam. So make sure that you can try to dissociate this. Now, I've got 3 more examples here. I more than welcome you on your example sheets to pause the video and attempt these next ones, and then resume the video. All right, so looking at the next one, we have potassium nitride. And it's also a good idea to practice naming these compounds. The potassium, okay, that is a metal, and it has a +1 charge. And the nitrogen, or nitrite in this case, has a -3 charge, and we have 1 of those. Okay? And what's the Van Hoff factor for B? Very good, 4. And again, if you don't know what that means, don't worry about it. That's not this topic. All right, letter C, we have iron 3 chloride. And the charge on the iron is +3 in this case. It can be either 2 or 3. Don't need to know that. When this breaks apart, we have the iron, the +3 charge, And we have 3 chlorines. Now, I didn't mention it up here. Why do I not have a 2 there for the nitrogen? That's right. Any time that we have nitrogen in its elemental state, okay, in other words, how we would find it in nature, well, we would not find nitrogen ions naturally in state in air. We can only find that in a solution. So like chlorine, we put chlorine in our drinking water all the time. You have it in your swimming pool if you have a pool in your backyard. This is what helps kill bacteria. Chlorine ions. It's not chlorine gas, it's chlorine ions. So when you place that solid powder in your swimming pool, or you see somebody put a powder in there, typically there's a metal attached to that. Usually it's hydrogen. Okay, so sometimes it could be sodium, which is very odd if you have a salt water swimming pool, and I know some of you have recently put some of those in. It's the chlorine that's killing the bacteria. The sodium and the hydrogen are used to measure how much chlorine's present. So when you check the pH in your swimming pool, you're not really checking how much hydrogen you have, but directly you're looking at how much chlorine you have, because it's a 1-to-1 ratio. So however much hydrogen we have, whatever the concentration is in your swimming pool, that's what your concentration of the chlorine is. So, and we'll talk about that when we do acids and bases as well. All right, if you haven't attempted any of these yet, try D on your own. Pause the video. All right, so you've had a chance to try it. So you have strontium carbonate. And again, carbonate has a -2 charge, therefore the strontium has a +2 charge, and we have a 1-to-1 ratio. So strontium's +2, carbonate is -2. Okay, so again, looking at these, all this first part is to get you familiar with the dissociation. You must be able to dissociate. Okay, these are ionic compounds or electrolytes, whichever way you want to call it. And again, we'll talk about electrolytes as being a particle that can carry a charge. All right, number 2. Calculate the molarity for a 184.6 milligram sample potassium dichromate. Dichromate, the Cr2O7 with a -2 charge, that's not one of your 10 polys. Don't have to worry about it. It's dissolved in enough water to make 433 milliliters of solution. So it wants you to calculate the molarity. Again, for refreshing, or to refresh your memory, if you look on your equation sheet, I'm pretty sure molarity is on there. I'm not 100%. I may be wrong on that. Molarity, again, is the number of moles of your solute, the thing being dissolved, over your volume, typically in liters, of your solvent. Okay? Solvent is a thing doing the dissolving. All right, typically we say that water is the universal solvent. In other words, especially for us, for humans, we want a lot of things to be water soluble, especially if we are going to ingest it or eat it or drink it. We typically don't want to eat too many things that are not water soluble. But again, that's more of a different issue. All right, so calculating molarity, we need to find out how many moles we have, and then we'll divide it by the total volume. Well, let's start off with the volume, since that's the easiest of them all, and we don't have to do any real calculations. But the volume in this case, we have 433 milliliters, and if I want to convert that to liters, how many milliliters are there in a liter? Okay, that's right, there's 1,000 milliliters in a liter. So really, I don't even need to get my calculator out to do this. So I have 0.433 liters. Okay, now I have to do a little bit of work here for my potassium dichromate. All right, so if I'm given milligrams, and I can leave this equation as is right here. Okay, so I'm going to actually put the 184. Now, if you want to do this as a separate equation, I have no problem with that. And this is of the potassium dichromate. What we want to do is we want to first convert the milligrams to grams, and then the grams to moles. So I'm going to go milligrams to grams. Which of these is bigger, a gram or a milligram? That's right, a gram is bigger. How many milligrams are in a gram? That's correct, 1,000. Okay, so there's 1,000 grams in a kilogram. There's 1,000 milligrams in a gram. especially if you're going to go into medicine. That's probably one of the conversions or those two conversions you really, really want to master or memorize. All right, now we need to convert this to moles, and you'll notice, hey, I've got my units, moles per liter, because milligrams are going to cancel out. Grams are going to cancel out because I'm going to find the molar mass of the potassium dichromate. So let's look at the periodic table. Potassium, which is right here, 39.1. And I have two of those, so 39.1. I'm doing this on my calculator on the side here. And then I have two chromiums. So chromium is 52. So I have two of those. Times that. Plus I have 7 oxygens. So 7 times 16. So my molar mass for the potassium dichromate is 294.2 grams. Now the nice thing is my units cancel out. I'm left with moles per liter. So that actually gives me my molarity. So let's type all that in. So I have my molar mass already in my calculator, so I can multiply that times 1,000. I'm multiplying everything on the bottom first. Times 0.433. That's going to give me a value. I'm going to keep that in my calculator. I'm going to use my answer button. So I'm going to take 184.6, divide that by my answer, and I get 0.0014, we'll say 5. And that's molarity. Now, let me double check that calculation just to be sure here. So 184.6 divided by, and I'm using parentheses, 0.433 times 1,000 times 294.2. Yep. Okay, so I'm sticking with that as my answer. So there's my molarity. Okay? Alright. Now again, don't freak out because there's really small numbers or really big numbers. You'll get used to that. Alright, number 3. Alright, describe how you would prepare or give instructions for the preparation of 7 liters of a 0.75 molar potassium chromate from solid potassium chromate. Okay, so this is a little bit different. This isn't the dichromate. The dichromate is the Cr2O7. And again, chromate here itself is not one of your polyatomics, so you don't have to worry about it. But this does have a -2 charge. That's why we have 2 potassiums. Alright, this is our one time that we get to write a sentence while we're working out a problem. However, if I'm given, or you're actually going into the lab and you have to prepare this solution, you know you need to make 7 liters of this, and it has to have a molarity that's 0.75 moles per liter, or molarity, and you've got a container of solid potassium chromate. How are you going to determine or know how to make this solution? Well, first of all, we have to understand what molarity is. And again, molarity is moles per liter. So if you're given a container of potassium, solid potassium chromate, how are you going to find out how many moles you have? That's right, you need to find out your mass needed to determine the number of moles. However, since we're not looking for 1 liter of this, we're looking for 7 liters, we get to do some further calculations. Now, what's really important here, and this is a great strategy, if you're ever given a volume and a molarity, and I think we talked about this in the last homework or last lecture here, that if you're given a volume and something that is associated with that volume, you always start with the volume. So in this case, we know the volume and the molarity. Therefore, you have to start with the volume. So I'm going to start off with 7 liters because that's what I want to make. Again, I need to know how much of this stuff I need. So I'm going to make 7 liters of this. So I know my volume, I know my molarity, so 0.75 molarity. And that's moles per liter. Don't ever write big M within your problem here. Alright, so if I stopped right there, that would tell me how many moles of the potassium chromate I need. You wouldn't need 0.75 moles. You would if you only had 1 liter, but you're making 7 liters of this stuff. Okay? Now, to be able to measure this out, I need to be able to weigh it out. And there's no such thing as a mole scale. However, there's a gram scale that I can use. And that's what I want to use. So I want to convert these moles, because if I stopped right now, my liters would cancel out, I'd have my number of moles. So now I need to find out how many grams I actually have of the potassium chromate. Okay, so potassium, again, has a molar mass of 39.1, so that's 2 times 39.1 plus 1 chromium, that's chromate. Whoops, didn't mean to do that. So add 52 to that number, plus we have 4 oxygens, so 4 plus the 4 times 16. So that gives me a molar mass for my potassium dichromate as 194.2. Now again, this should be a different mass than the problem above because that was potassium dichromate. This is just potassium chromate. Alright, so now what I'm going to do is I'm going to calculate this all out. My moles will now cancel out and I'm left with grams. Now I have something that I can use to measure out to make this solution. So I have my 194.2 grams in my calculator, so I'm going to multiply that times 0.75 and then multiply that times 7. So that means I need 1,000, and we do not want to round this number, 1,019.55 grams of potassium chromate. Okay, so now we get to answer the question. Give instructions. Describe how you would prepare this. All right, so here's what we need to do. We need to place 1,019.55, yep, put all those in there, 1,019.55 grams of what it is, potassium chromate, K2CrO4, in a volumetric flask. Okay, and I'll show you what a volumetric flask is when you all return to school. So a volumetric flask, and it's specifically made for making solutions. So this is really neat. And we only use this volumetric flask when we start with a solid. You won't use this volumetric flask when you have liquids. Okay, so volumetric flask, and then add enough. Okay, this is really important. Add enough water so that, scroll this up a little bit, so that the total volume is 7 liters. Okay, so some really important things here. You got to tell me how much of what it is, add enough water, total volume. Okay, now here, this is what I want to just emphasize here. If you were given a container, okay, this is not a volumetric flask, and I'm not an artist. All right, actually, I can draw that probably a little better than that. Okay, erase. Okay, so we have our container in this case, and we'll put our 1,000 grams of our substance in here. And my container here says that I've got 7 liters at that point right there. Okay, so along that mark right there, 7 liters. If I take a container and I pour in exactly 7 liters of liquid in there, will my volume of water come right up to 7 liters? Hopefully you're saying no, because we have this solid already in here. So it's already occupying a volume. And if you just go ahead and take 7 liters and dump it in there, you're most likely to get a volume that exceeds 7 liters. So what we want to do, and again, what we need to have is we need to have a solution that has exactly 0.75 moles for every liter of this solution. So that's why I emphasize on here, make sure that we add enough water so that the total volume is 7 liters. Now we're not adding 7 liters to our 1,019.55 grams. You add just enough water. Okay, mix it up. Make sure that the level comes to exactly 7 liters. That way you're ensuring that when it's properly mixed up and it's allowed to dissolve into its electrolytes, then we'll have exactly 0.75 moles for every liter of solution we have. Isn't that cool? All right. All right, number 4. A little bit different here. Describe how you would prepare or give instructions to form 7 liters of a 0.75 molar potassium chromate from a 2.25 molar potassium chromate stock solution. Now, here's what I want us to look at right now. Here you've got your, come on. Here I've given you a graphic, and I'm pretty sure that I gave you this graphic. Our stock solution, okay, our stock solution right here, besides that, our stock solution is a more concentrated solution. In other words, it has a much higher molarity than our dilute solution. Okay, and I'll talk about what little beaker is here in a second. Our dilute solution is a solution that has a certain number of moles of the material that we're trying to get, but we've added water to it. And you'll notice that the color of the stock is much different than the color of the dilute. Now, here's something that's really, really important. Okay, and I want you all to be able to see this. That when we look at the little beaker, and this is actually what we're going to do. We're going to focus on little beaker here. And you're not going to find little beaker in any chemistry textbook or anything. That's a Kriegerism there. So what I'm going to do is I'm going to look for a volume for little beaker, and I want to find out how many moles I actually have within little beaker. Because when I find out how many moles I have in little beaker, it's going to tell me what the molarity of my stock is. And if I know what my molarity of my stock, and I know exactly how many moles I have in little beaker, then it will definitely help me to calculate the dilute solution. Okay. Now, I did make a separate video explaining how to make a dilute solution from a stock, and I'll post that online as well. But I'll do my best here to explain little beaker here for you. All right. So describe how you prepare 7 liters of a 0.75 molar solution from a 2.25 molar stock solution. Okay. So the key here is, first thing that we need to do is we need to find out, again, how many moles. Okay. So if we know how many moles we have, just like up here, okay, we found out how many moles we had. But we went one more step and found out the grams because we had a stock solution. But the neat thing is, this type of problem is a little bit easier. I'm telling you, it seems more complicated, but it is a lot easier. So the first thing that we want to do is we want to find out how many moles we need. Actually, let me get that pen. So we want to find out how many moles we actually have in the dilute solution. Okay? That's the first thing that we need to do. So we know the volume. We know the molarity. If you know the volume and the molarity, always, always, always start with the volume. So we're going to take our 7 liters, we're going to multiply that times our 0.75 moles per liter, and again, my volume cancels out, and whatever 7 times 0.75 is, some of you probably can do that in your head, that tells me that I have 5.25 moles of potassium chromate in my, or that I need to make my dilute solution. So okay, so now I know how many moles I actually have in my dilute solution. That's important. Because now what I'm going to do is I'm going to go and measure from the stock how much, okay, volume-wise, what volume of little beaker I need to get that number of moles. Pretty cool. Okay? So here we go. I know the moles, and I actually know the molarity of my stock, so I'm going to figure out what volume of little beaker I need to make this dilute solution. So I'm actually working backward. So I know I've got a 2.25 molar solution, stock solution bottle on the shelf, and I need to make a 0.75 molar solution. Okay, so I know I need 5 1/4 moles. So if I know I need 5 1/4 moles, I'm going to start with that. Now, the neat thing is molarity, it's a value, or it's a unit that has, it's a derived unit. In other words, it's moles per liter. So molarity, again, is moles per liter. It just means that it's the number of moles per volume. Okay, in this case, 1 liter. We can use this to help us determine what the volume of little beaker is. So again, whenever we do factor labeling, if it's not the unit we're looking for in our final step, we're going to move that unit down. Okay, so I want to get rid of moles. Erase that circle there. Okay, so where in the world can I get a value for moles here? Well, right there. Since I'm looking at volume and molarity here, I'm sorry, volume and moles, which is my molarity, I'm inverting the molarity so that I cancel the moles out and I'm left with the volume. And that'll tell me exactly the volume needed for little beaker. So I'm going to put my 2.25, again, from there, 2.25 moles for every 1 liter. Okay, isn't that cool? So now my moles cancel out and I'm left with my volume, which will tell me exactly what volume I need for little beaker. Awesome. So let's go ahead and calculate that out. So 5 1/4, I have that still in my calculator. Divide that by 0.225, and that gives me 2 1/3. So 2 1/3, or 2.3 repeating liters. Okay. So there we go. We've got our volume. Now we can write the instructions. All right. So here we go. We are going to place 2 1/3 liters, and again it's a 2.25, 2 1/3 liters of a 2.25 molar solution of potassium chromate in a flask. Okay, so I have 2 1/3 liters. Boy, that's very easy for me to say. Of a 2.25, and if you want to say molar or stock solution, that's fine, in a flask, and then add enough water. Again, it's that add enough water again. I guess we could use a volumetric flask here. In a volumetric flask, add enough water so that the total volume, so that the total volume is, what are we making? 7 liters? 7 liters. Is 7 liters. Okay. All right. So again, this time, since we have and again, we have to recognize that if you have a stock solution, that means that you have a liquid. Okay? If it says that you have a solid, that means you have to find out the mass. Okay? All right, so again, we want to calculate what volume is needed. We need to find out what volume is needed of little beaker from the stock so we can get our number of moles. Okay? So recall that the number of moles here for the little beaker and the dilute solution do not change. No matter how much water you add to this dilute solution, the number of moles within that dilute solution will not change. However, the molarity will change as you change how much water you add to this. Okay? Looking at the stock and little beaker, the molarity is the same. And again, when we talk about molarity, we're talking about moles per liter. So it doesn't matter if I have, say, a 7-liter container of my stock, and I only take maybe 10 milliliters of that. I guarantee you I'm going to have the same concentration. If this is a 2.25 molar solution, this little beaker will also have a 2.25 moles for every liter, even though we don't have a full liter there. Okay, so what's really cool about this graphic is when you look at the stock and little beaker, the molarities are the same. When you look at dilute and little beaker, the number of moles are the same. And we need to know how many moles we have so we can find out what volume is needed for little beaker. Sorry about that. I should have left it as a Word file. Okay, so we want to emphasize the volume from my stock, and then, again, add enough water and your total volume. Those are really important statements to have in your answer there. All right, number 5. Okay, this is the big kahuna right here. Number 5, it says a stock solution containing barium ions was prepared by dissolving 23 grams of pure barium metal in nitric acid and diluting to a final volume of 2 liters. Calculate the concentration of the barium ions in the stock solution and the dilute solution if 125 milliliters of the stock solution was diluted to 500 mils. Okay, so here's what we're going to do. We're going to first prepare a stock solution. Okay, so we want to make a stock solution. So we're taking 23 grams of pure barium metal. Okay, so 23 grams of barium metal. Now, don't get hung up that it has a +2 charge over here. Again, removing 2 electrons is not going to change the molar mass by any significant amount. So we have 23 grams of barium. Okay, let's find out what the molar mass of barium is. Barium's down here, right there, 137.33. So 137.33, and that's grams per mole. So that gives me my number of moles. Now, if I want to, I could include the volume in here so that I go straight to molarity. So my grams would cancel out. Whoops, my grams would cancel out, and I'd be left with moles per liter. And I'm going to do that. If you need to show it in 2 steps, in other words, calculate how many moles you have, then divide it by the volume, that's fine. We can do that. All right, so we're going to take our 23, divided by, open up your parentheses, 2 times 137.33, close your parentheses, and that gives me point 0.083, we'll go 366 here. So 0.0837, and that is our first part of this problem. We just calculated the molarity of our stock. Okay, so there's your concentration for your stock. Not hard. Just you have to keep asking yourself. Again, this whole year, you're going to be asking yourself questions about, what is this question asking? What do I need to get the answers needed? And sometimes it's just this simple. Sometimes it's a little more complicated. You have to understand what you're given and what you're looking for. That's huge, because I hate to say it, this isn't a chemistry class. This is a problem-solving class. And I want you all to be very, very good problem solvers. Because again, that's what life is, unfortunately. All right, so we answered the first part of the question. Now it says calculate the concentration of the barium ions in the stock solution. Did that. And the dilute solution if 125 milliliters of the stock solution is diluted to 500 mils. All right, so we have our 2 liters, and we really don't care that we have 2 liters. We just know that we're taking 125 milliliters of this. So I'm going to ask you, do we know the 2 important ingredients here to answer this last part? The answer is yes. You know the molarity, which you just calculated, and you know the volume that you're taking. If I know the volume and the molarity, what will that give me? That's right, it'll give me the number of moles. Okay? And that's what I need, because again, I need to find out what my dilute solution is by calculating the concentration. Concentration is molarity. So my final volume is going to be 500 mils. But first, I'm not gonna look at that one yet. Don't look at that yet. Focus on the 125. So for my dilute, okay, my dilute solution, I have my volume, which is 125 milliliters. That's not a number that I like, so I want to convert that milliliters into liters. So 1 liter, there's 1,000 milliliters in there. And then I'm going to plug in my molarity. Again, I'm not going to use a big M within the dimensional analysis portion of this. So 837, and this is moles per liter. Okay, so my milliliters, goodbye. My liters, goodbye. So I'm left with moles. Okay, so if I type all that in, I've still got my value here in my calculator. So I'm going to type that times 125, and then I'm going to divide that by 1,000. So this gives me, and again, we could do this last step in 1 step, but I'm going to go slow here. 0, 1, 0, we'll say 5 moles. Okay. Now, is that what the question's asking for? How many moles are in my dilute solution? No. However, That tells me how much I have in my little beaker, which happens to have a volume of 125 milliliters for my 2-liter stock solution. So if I know what my volume is here, don't I know how many moles I have? That's what I just calculated. So now I can calculate the final molarity of my dilute solution. Okay, I know the moles. So if I know the moles, I can now calculate what my final molarity is, because I'm going to take that 0.015 moles and I'm going to dilute it to a total volume of 500 milliliters. So I'm going to take my 0.0105 moles and divide that by my volume. Molarity is moles per liter. So 500 milliliters. Convert that milliliters into liters. So there's 1,000 milliliters in a liter. So now milliliters cancel out. I got my moles per liter. So I still have that number in my calculator, and it's good that it's still in my calculator. I don't want to retype in and get 0.0105. So I still have my 0.01046747 in my calculator, and I'm going to multiply that by 1,000, and then I will divide that by 500. So this gives me a final molarity of 0.0209, we'll say. And that's my molarity, my dilute molarity. All right, before I scroll up, one thing to remember about dilute solutions, and this is a real quick check to make sure that you're actually doing this right. The reason why this has a lighter color than the stock is because there's more water in this, and it will get lighter in color. Think about this. If I were to take this 500 milliliter solution of my dilute and walk over to a large pool, even though this is green, I pour that into the pool, will I see that green color very well after it's had a chance to spread itself out throughout the pool? Absolutely not. Not unless the water's already green. So if it's a clear solution and I pour something green into that, and it's a very large volume, it's going to get even less green. Okay? So the more concentrated, it should be darker. That should be a real quick check for you, especially when you're in the lab doing something like this. Therefore, my dilute concentration should also be lower than my stock. My stock was a 0.08. My dilute was a 0.02. And both of these are molarities. So that's a real quick way to check and make sure that you're actually doing your work correctly. If you find out and you do calculations and you find out that your dilute concentration has a higher concentration than your stock, something's not right there. Okay, so these are some things that you have to be thinking about while you're working these problems out. All right, I think that was the last example. And again, if you have any questions, don't hesitate. Please email me. Let me know how you're doing here, guys. And I don't believe that we talked about dilute concentrations or dilute solutions in general chem. So this is one of your first brand new topics. And I hope you're watching the videos, because I don't think you're going to get it if you just check out the answers and go, what did I do? All right, again, I hope this video's helped.